Tem um adaptador? Me empresta. Não é HDMI. Eu tenho... Não. Eu tenho um pendrive. Aqui. Não, volta. Aqui. Essa daqui. Não. Só tem o LibreOffice? Ou tem? Tá bom, tudo bem. Bota aí. Pronto. Ok. Well, thanks for the invitation. It's really nice to be here. Such a wonderful place. So, I'm going to talk about this result we got in 2017. Coherent blue emission generated by rubidium, two-photon excitation using diode and femtosecond lasers. Those are the authors. Well, first let me define the physical problem. Okay, it's a very simple thing. You have rubidium-85. Those are the transitions involved. Basically, you have a CW laser over here, and a femtosecond laser, a mode-locked laser there. And then you have this 420 nanometers coherent blue light being generated by a full-wave mixing process. The interesting thing about that is how the modes of the femtosecond comb can shows a signature in the coherent light generated by the blue light, the generated blue light. So here the experimental setup is really simple. We are talking about a titanium sapphire laser, a diode laser. They're both combined a beam splitter. They are collinearly passing through a rubidium vapor cell. And then we look at the full wave mixing signal here. And to make sure that we're not looking at the fluorescence, we also look at the side of the cell. So we also look at here. Then you have a spectrometer and a PMT to do the actual measurements. So let's talk about the results. Here is the vapor cell, here is the signal as we see in the experiment. And then right here you have a blue intensity light. We all the time, I didn't mention before, but all the time we are going to look only to this signal here, okay? Above we have saturated absorption, as everybody here knows or has experience with. And then we have here the blue, the coherent blue sign. Here we sweep the diode frequency. And then you have 3 peaks. These 3 lowest peaks are due to the fluorescence, induced fluorescence by both lasers. And the highest peak is the parametric full wave mixing signal. So, but how can we tell that? First we look at the Fluorescence signal is the inset signal there, green. We look at the side of the cell. And then we look at the full wave mixing signal, is the blue one. And we cross the polarizers to see if we can reduce this background signal to the fluorescence itself, and we can. So this shows that the fluorescence is not polarized nor directional. The highest peak, due to the full wave mixing process, has a polarization, and it is directional. One question we had back then was how the atomic density plays a role together with the comb modes, okay? We do have an indirect way to control the atomic densities by playing with the temperature. So we heat up the cell, and then we start with 72 Celsius degree. We basically have fluorescence there. And as we heat up, we start to see that one comb mode shows a peak here due to the full wave mixing process. And as you heat up even more, you have a higher atomic density, then you have more modes showing up here. You have two modes here. As you go to 87, you can see that you have more modes, but they are blurred due to the saturation of the signal, and also we sweep very fast. So in the next slide, I'm going to show, to zoom in this signal here, sweeping more slowly and doing an average to show the signature of the modes there. So here they are. We have the blue curve is the experimental data, and here we have this green Gaussian curve, what's basically the fluorescence. We have a Doppler width of 500 megahertz, and then we have these small Gaussians here for each mode, okay? And then we have about, the black curves, they have about 55 megahertz, and they are enlarged by power broadening and jitter of the comb. So the red curve is the sum of the green and black. It indicates clear contribution of each frequency comb mode on rubidium, on this coherent blue light. Whoop. So, it's important to look at the atomic density versus the peak of the signal. We got the peak of the signal for different temperatures or different atomic densities and plotted. These two curves are different because the intensity of the diode is higher on the red one and is lower in the blue one. So for the blue one, there and here, we see a threshold behavior like atomic density behavior and saturation. The red one, if you start with a very high intensity of the diode laser, you actually have a stark shift in the beginning, what inhibits the two-photon excitation process. So you have almost nothing here, but then it recovers as we have higher atomic densities. We did a small, a very simple model back then. We had 4-level systems, interaction Hamiltonian with electric dipole approximation using Maxwell-Bloch equations, and we tried to reproduce this result here. And looking at the Rabi frequency of the coherent blue light, and changing the intensity of the diode, CW diode laser there, as the optical depth of our sample changes. So it's kind of similar and qualitatively explain our results, corroborates our results. So almost done. So here's my hometown. University is there, so it's 300 kilometers south. Just go by the coast here. You can see Natal over there. No, you can't. But it's also a coast town. Here's my lab. It started in 2014 like this. October 2017, and then I asked the student to send me a picture. He didn't took a very good picture, but it's like this. We're setting up a lab there. Those are the experiments. Okay. Well, I know them by heart. I do have a frequency comb, a TICEF laser, another frequency comb, a terbium fiber comb, ultra-stable cavity that can give me lines under hertz. And I'm buying parts for a rubidium cesium MOT to do direct frequency comb spectroscopy, molecule creation, coherent control, stuff like that. So the first two combs are working. We have our first results in the terbium fiber comb. All of them are homemade. And here is my group, Optical Metrology Lab. Me, this picture is a while ago. I still had hair back then. Lucas and Cecilia are PhD students. Ido and Naldson are undergrads, so here's my contact. And that's all I had to say. Thank you very much for your attention.
Thanks, Marcio, for your talk. Questions from the audience? Yes.
Marcio, from the measurement that you